Welcome to this session. In this session, we'll be talking about the basic concepts of recurrence relations, the solving of recurrence relation. That's the next part of this recurrence relation saga. We'll talk about in subsequent sessions. So let's begin. Say for example, we have a series of numbers. Say for example, we have the simple series, let us say 1, 2, 3, 4, 5. Or let us say we have a series, let us say 1, 4, 9, 16, 25, and so on. You can easily identify that this is the series of squares of these numbers. So when we have a series of numbers, we want to find out the nth term of a series. Say for example, if I am designating this series by let us say S, then we need to know the nth term of the series. So I can identify the nth term of the series. In this case, this is pretty simple. The nth term of the series is simply n. Similarly, if I want, let us say this is designated by let us say t, and I want to find the nth term of the series t, this is simply n square. So when we have a series of number, in a nutshell, when we have a series of number, what we are trying to do is we are trying to identify a formula or an expression for the nth term of the series. See, these are simple examples that I've shown you. Here I can easily identify an expression or a formula for the nth term of a series. But sometimes it so happens that it is not as easy to identify the expression for the nth term of the series. There, what we do is we try to find the expression for the nth term of the series in terms of its previous terms. Say for example, if I specify, let us say the series, let us say 3, 5, 7, 9, 11, and so on. Now if I try to find the expression for this series, let us say this is designated by x. Now I want to find out the n. So nth term of the series, if I now found out. So if I want to find out the expression for the nth term of the series, now it is easier to specify the nth term in terms of the previous terms along with the initial value. It's easy to specify the nth term of the series, like we can specify that the first term of the series is, let us say, let us designate it by x0 is, let us say, 3, and each subsequent term can be obtained by taking the previous term and adding 2 to it. So I can specify that the initial condition x0 as 3, and then I can specify that each subsequent term can be obtained by adding 2 to the next previous term. So this is what is actually a recurrence relation. So in a recurrence relation, what we are doing is we are specifying the nth term of a series by using the previous terms. We can use one previous term or two previous term. The most common example of specifying the recurrence relation can be the Fibonacci series. So we all know what is a Fibonacci series. Fibonacci series 1, 1, 2, 3, 5, 8, 13, and so on. We know that the Fibonacci series, every term is the sum of previous two terms. So I can specify the, let us say, xn is equal to xn minus 1 plus xn minus 2. This is the nth term. It is the sum of just two previous terms. But I cannot obtain these two terms by using this expression. So these two terms will be used as the initial values. Let us say x0 is equal to 1 and x1 is equal to 1. So this is what a recurrence relation is all about. We specify the recurrence relation by specifying the nth term in terms of the previous terms and initial conditions. Next, let's talk about the order of a recurrence relation. See, the simplest recurrence relation would be one where every term is dependent only on the previous term. Say for example, if I have the series like, let us say 1, 2, 4, 8, 16, 32, and so on. So I can simply say, let us say this is the series A. So I can say AN is equal to 2AN minus 1. That means each term can be identified or each term can be obtained by simply multiplying the previous term by 2. And I will specify the initial condition like, initial condition is specified like, I will specify, let us say this is the initial condition, A0 is equal to, let us say, 1. So the first term is 1 and the remaining terms can be obtained by simply multiplying the previous term by 2. So if A0 is equal to 1, A1 can be obtained by simply multiplying 2 into A0. So I'll get 2. So A2 will be obtained by multiplying A1 by 2. So I'll get 4 and so on and so forth. So this is the simplest form of a recurrence relation where each term is dependent only on the previous term. Such recurrence relations are called recurrence relation of the first order. See, I have shown another example. That can be xn is equal to 1 is xn plus 1 is equal to 2 minus xn divided by 2. See, I can specify the recurrence relation in both the manners. I can either specify the nth term in terms of n minus 1th term, or I can specify the n plus 1th term in terms of the nth term. See, both these are perfectly valid. But the point to be noted over here is each term is dependent only on its previous term. Xn plus 1 is dependent only on xn. So this is called the recurrence relation of first order. Or we can also say that the order of this recurrence relation is equal to 1. Now, on the other hand, we can have higher order recurrence relations also. Say for example, if I have a recurrence relation which depends not just on the immediate previous term, but on, let us say, two previous terms. The best example would be the Fibonacci series. In Fibonacci series, each term, let us say the term is xn, is equal to the sum of the previous two terms, xn minus 1 and xn minus 2. So here each term of the series is dependent on not just one but two of the previous terms. So here we say that this particular recurrence relation is of order 2. So essentially speaking, what do we mean by the order of a recurrence relation? The order of the recurrence relation can be understood in two ways. One, how many previous terms of the series are being used to find out the nth term. Or if I want to formalize the statement, I can say that the order of the recurrence relation is the difference between the highest and the lowest subscripts of the relation variable. Say for example, I'll show you three examples. Let us say I have a recurrence relation 13AR plus AR minus 1 is equal to 0. So here I can immediately see that the expression AR is dependent only on one previous term. So it's of order 1. Or I can find out by simply taking the difference of the two subscripts. See over here, R, one subscript, the largest subscript, and the smaller subscript is R minus 1. So the difference is 1. So this is a recurrence relation of order 1. If you see over here, the highest subscript is fx, the lowest subscript is fx and the highest is fx plus 2. So the difference over here is, this is x and x plus 2, so the difference will be 2. So this is the expression, it's a recurrence relation of the order 2. Similarly, I can see it over here, n plus 2, n plus 1, n. So this is the largest subscript, this is the smallest subscript. The difference between the two gives me the order of the recurrence relations, that is 2. So this is how you will find the order of the recurrence relations. Next, when we are generating the sequences based on recurrence relations, now we can use recurrence relations in two ways. One, if I have been given a series, I may be asked to use the series to identify the recurrence relation. As I've shown you earlier also, say let's once again take the example of Fibonacci series only. I have this 1, 1, 2, 3, 5, 8, 13, 21 and so on. So I can say an is equal to an minus 1 plus an minus 2, and I can say that a0 is equal to 1 and a1 is equal to 1. So these two are the initial conditions. So if I have a series, I can use this series to find out the recurrence relation, or I can go in the reverse direction also. Suppose I have this recurrence relation and I have these initial conditions. So I can use this recurrence relation and these initial conditions to find out the series. So to generate the sequence based on recurrence relation, one must start with some initial values. These must be given in order to identify the sequence. So recurrence relation if you have, but if you do not have the initial values, then it is difficult to identify the series from the recurrence relation. Why? Because let us say if I give you a recurrence relation like, let us say an is equal to an minus 1 plus 2an minus 2. Now if I ask you to identify the series which this recurrence relation is identifying, now the problem in identifying the series is, where do I start the value of n? Do I start the value of n at, let us say, 0, or do I start the value of n at, let us say, 1 or 2 or 3 or 4 or what? So to identify the sequence from the recurrence relation, it is very important, very necessary to have the initial values. If you have a recurrence relation of order 1, only one initial value is important. If you have a recurrence relation of order 2, then you must have two initial values and so on and so forth. Next, let's talk about the degree of recurrence relations. The degree of the recurrence relation is simply the highest power of the recurrence term. The highest power of the recurrence term. If you see this example, here 3xn plus 2, 4xn plus 1 and 3xn. These are the recurrence terms. Xn plus 2, xn plus 1, 3xn is equal to 2n. These are the recurrence terms. Sorry, this is not the recurrence term. These are the recurrence terms. And what is the highest power of these recurrence terms? 1. So this is of degree 1. Say for example, if I change this recurrence relation to, let us say, 3xn plus 2 plus 4xn plus 1 plus 3xn is equal to 2n cube. Still the degree of this recurrence relation will be 1. Why? Because the highest power of the recurrence terms is still 1. This is not the recurrence term. So we only use the power of the recurrence terms. If you see over here, this is the highest power is, this the power has 3, this has the power 2, this has the power 1. So the highest power is 3, so the degree will be 3. Similarly here, the recurrence term has the power 4, here 3, here 2, here 1. So the degree of the recurrence relation is 4. A recurrence relation of degree 1 is called a linear recurrence relation, and will be focusing on linear recurrence relations only in this particular subject. Let's take a couple of examples to understand the concepts of recurrence relation, whatever we have talked about till now. Find the first four terms of this recurrence relation. See, this is a recurrence relation of order 1 and degree 2. See, order is 1 because the difference between the highest and the lowest subscript is 1. And the degree is 2. Why? Because this particular term is having the power 2 over here. And we have been given an initial condition a0 is equal to 1 over here. So if a0 is equal to 1, we can very easily find out the first four terms. A0 is equal to 1. Let's put 0 over here. So a1 is equal to a1 minus 1 whole square. So that is a Again 0 whole square. So that is equal to 1 square, that is equal to 1. A2 is equal to A1 square, which is again equal to 1. Sorry, I have taken an example where all the terms are coming as 1. So the series here will be 1, 1, 1, 1 and so on. Let's take another example. My mistake, I took a example where, sorry, let's take another example. Let's say an is equal to an minus 1 plus 4 a0 is equal to 1. Let's take this recurrence relation, and now I want to find out the first four terms. So now I have a0 is equal to 1, a1 is equal to a0 plus 4, that is equal to 1 plus 4 is equal to 5. A2 will be A1 plus 4, that is 5 plus 4, that is 9. A3 will be A2 plus 4, that is 9 plus 4, that is 13. A4 will be 13 plus 4, that is 17, and so on and so forth. So this way you can, if you have been given a recurrence relation and an initial condition, you can find out the series. So the series over here is 1, 5, 9, 13 and so on. Let's take another example, a slightly different example. Show that the sequence 2, 3, 4, 5 up to 2 plus n for n greater than equal to 0 satisfies the recurrence relation, given recurrence relation for n is greater than equal to 2. Right? So let's see this. Now for solving this particular question, we will go in the other way around. So we know that an is equal to 2 plus n. This is known to us from the series that have been given. So the nth term of the series is 2 plus n. So an I have got. What I will do over here is I have the value of an. Now I will use the value of an and this series to identify an minus 1 and an minus 1 2, and then I will put these expressions over here and verify that LHS is equal to RHS. So now an minus 1 will be equal to 2 plus n minus 1, that is equal to 1 plus, and an minus 2 will be 2 plus n minus 2, that is equal to n. Now I've got the values of an minus 1 and an minus 2. Now let us put all these three values in this expression. So an is equal to 2 plus n is equal to twice of an minus 1, that is 1 plus n, minus an plus 2, that is n. So let's solve the right hand side. I get 2 plus 2n minus n. So I get 2 plus n. LHS was also 2 plus n. So left hand side is equal to right hand side. This is one way of doing this. Or what you could have done was you could have used just the LHS to show that LHS, the RHS, this was the RHS, it has come as this value which is same as AN. So left hand side is equal to right hand side. So I can say that this particular series that has been given to us, this series that has been given to us satisfies the recurrence relation. So if you have been given a recurrence relation, you can use this recurrence relation to identify the series. If you have been given a series, you can try to find out the recurrence relation. And if you have been given the series and the recurrence relation, you can try to verify that the series verifies the recurrence relation or vice versa. Now the next, let's talk about the coefficients of the recurrence relation. Now, when we say coefficients, we are talking about the coefficients of the recurrence terms. See, in these examples, these are the recurrence terms. So, the coefficients over here are 3, 4 and 3. Now, these are constant values. So this is called a recurrence relation with constant coefficients. Whereas if you see over here, this coefficient is 3, but this coefficient is no longer constant. The coefficient over here is n, and the coefficient over here is n square, which is once again the variable. So here this is a recurrence relation with non-constant coefficients. Next, the next categorization is homogeneous and non-homogeneous recurrence relation. If we represent the recurrence part of the relation by, let us say, Fn. If we represent the recurrence part of the relation by Fn, let us say this is the recurrence relation that is given to you, then this is the recurrence part of the relation. Let us say if I represent it by, let us say, Fk, this is an F, so this is Fk. So if I can specify Fk is equal to 0, in other words, if the non-recurrence part of the relation is 0, then it is called a homogeneous recurrence relation. And if the non-recurrence part of the recurrence, the expression that is given to you, say for example like this, then it is called a non-homogeneous recurrence relation. So in a nutshell, if the recurrence relation can be equated to 0, the recurrence part of the recurrence relation can be equated to 0, then it is called a homogeneous recurrence relation. Otherwise, it is a non-homogeneous recurrence relation. These are some examples. Say if I take this example, an is equal to 2an minus 1 plus 1. Now you can see this is a recurrence relation of order 1, first order. This degree of this recurrence relation is 1. So it is called a linear recurrence relation. The coefficients are, see the coefficients are, the coefficient of an is 1, the coefficient of an minus 1 is 2. So this is constant coefficients. But the non-recurrence part of this relation is not equal to 0. So this is a non-homogeneous recurrence relation. Let's take this example here. Once again, Bn n minus 1. So this is a first order recurrence relation. Once again, the highest power is 1. So this is a linear recurrence relation or degree 1 recurrence relation. But you can see the constant, the coefficient of Bn minus 1 is not constant. This is n. So this is non-constant coefficient, and I can write this as, let us say, Bn minus n Bn minus 1 is equal to 0. So the non-recurrence part is equal to 0. So it is called a homogeneous recurrence relation. We can take another example. Fn is equal to Fn minus 1 plus Fn minus 2. So this is a recurrence relation of second order. The coefficients are 1, 1, 1. So it is constant coefficients. Degree is 1. So it is a linear recurrence relation. And once again, the non-recurrence part of this is equal to 0. I can write it as Fn minus Fn minus 1 minus Fn minus 2 is equal to 0. So this is a homogeneous recurrence relation. Now, that's essentially all for today. I'll just leave you by giving you a basic idea of what do we mean when we say we want to solve a recurrence relation. Now, solving a recurrence relation actually means finding an explicit formula. I want to find out a formula which I can use to evaluate the nth term of a series without using the previous terms. Say for example, if I have the recurrence relation ak is equal to 2ak minus 1, where a0 is equal to 1. This is every term is 2 times the previous term. So I can specify it as ak is equal to 2 to the power k. Now here this expression for the kth term is not using any previous term. It is using the value of the index. So this is the solution of the recurrence relation. Now there are three methods of solving recurrence relations which we'll be seeing in the subsequent sessions. The first is the iteration method, second is the characteristic root method, and the third is the generating functions method. Now one important thing, if initial conditions have not been specified, then a recurrence relation can have multiple solutions. It is only by the use of initial conditions that the recurrence relation gets a specific response, a specific expression, right? So that's all for today. We'll talk about the different methods of solving recurrence relation in the subsequent sessions. Till then, thank you.